welcome back to our next video. In the last video, we started talking about confidence intervals and how some of the assumptions that were involved with dealing with those. But in order to do the confidence interval as we last described it, we had to follow very specific steps and adhere to very specific assumptions. So in this one, we're going to kind of expand on that notion, and we'll recap a little bit about what's going on. But we're going to look at some different types of intervals and some different types of confidence intervals that we can start to establish using the same basic methodology that we've constructed up to this point. So without further ado, we'll get ourselves going here. All right, so we're still in Chapter 7 of our book, Section 7.2. Okay, and we know from the last one that we had this restriction that for large N, the central limit theorem kind of gave us a model for modeling normally distributed, all right? And so the typical methodology, if you remember, was that we took a Z statistic, which was part of that standard normal table, and then we shifted our sample data off of that. So in this case, we're going to take the sample mean, I'm going to subtract the population mean, and then we made this be the sample standard deviation and divide that by the square root of n. This becomes our large N or large sample size confidence interval. Now, the thing that you'll notice here is that X bar obviously knows the sample mean, but this is the piece that changes. Okay, the stuff that we did before, I had to know the population standard deviation. Okay, now we're looking at, and it was located here. The rest of the formula is exactly the same, but now we're looking here and it's the sample standard deviation. Now that provides some variability into our samples because, depending on how you choose your samples out of the population, I mean, your results for this sample standard deviation could be very significant, okay, or they could be very insignificant depending on how they're chosen on this. So we want to kind of take a look at kind of some things that we can kind of start to do with it. The rest of the approach to what we did with this is very, very, or should be very, very familiar, all right? Okay, now, because we have a large N, the central limit theorem applies and basically says that, if I repeat a number of samples a certain number of times, the graph of the sample mean will start to tend to be normally distributed, and that doesn't change here. So we're going to be looking at an approximately standard normal distribution. Okay, and so the nomenclature that we had before, and if you need to review this, go back into our last video, and we'll kind of talk about some of the notation, but everything we define as a confidence interval of something like, oh, it's a 95% CI, and when I do that, here alpha is 5%. Okay, and so that's the way we write it as a 100 times 1 minus alpha percent. So if I plug in 0.05 here, I get 95. That's the nomenclature that they use. Okay, and so the confidence interval for a population mean of this percentage then was given by X bar plus or minus Z alpha over 2, multiplied then by the sample standard deviation over the square root of n. Okay, so it's exactly what we talked about in the last video, except now we're using sample data and not population data for the standard deviation. Everything else is pretty much exactly the same. Now, the thing that's cool about this is that before we talked about that sigma, sigma, versus S, we talked about this in the last video, is that this requires knowledge of the population. And normally we kind of fudge this in practice because we would go in and we would look at historical data or something and say, oh, I've been doing this for 40 years. I know where, I know what this value should be about. Okay, and so, but now, by not needing this guy and focusing on this is now based off of my current measurement. Okay, and so this becomes a pretty useful tool that now I have everything I need to calculate and I don't have to worry about this. So this becomes one of the big pieces moving forward is how do I get rid of an unknown population parameter and replace it with a sample parameter, but there's some corrections that have to happen along the way. This one for large N, central limit theorem bails us out and basically makes the formula exactly the same. Okay, so again, X bar is the sample mean and S is the sample standard deviation. There's no major changes there. Okay, you just have to have a large N to be able to do it. Okay, now, suppose that you want to find something that is not the population mean. You're not trying to predict that, but instead trying to predict a population proportion. Okay, so we'll kind of walk you through kind of a process, and I'll show you the formulas where this comes from, is that we can, we're going to go back to our point estimation techniques. Okay, and if you remember, a point estimate is basically a rule or a value that we use to estimate a statistic. Okay, typically we wrote this in our last video as being some theta hat versus a theta was kind of our argument. This was our true statistic we were in the population, and this is what we were using to estimate. And again, this could be anything. All right, so if you need to review this, we've got a video on point estimation. So again, go back and take a gander at that one, if you will, and where we talk about bias and those kind of things, and kind of this is the way we're going to set this approach up. So here's what we're going to do. So again, anything with a hat on it, the general version was to write it as thetas, but in this we've written it as a P to stand for the proportion, or kind of a probability, if you will, is that but the hat indicates that it's the estimator. Okay, and so if we do this, then our proportional estimate would be our random variable x divided by n. So this is assuming equal likely outcomes, and we're going to use that as an estimator of p, okay, where basically p is the number of successes in a population. So it's kind of like what we're doing with the binomial stuff on there, but this is, you know, a probability. Whenever time you see a proportion, we're actually talking about a probability. All right, so then based on our point estimate discussions, the estimate is said to be unbiased if the expected value of my p is equal to p, and then going through our math and our process on this, we can prove that the standard error for our proportion then is the square root of p times 1 minus p all over n will get us our standard error for this. Okay, now again, for an n large, p is approximately normal. Okay, and again, that's the central limit theorem work for us. This is a very powerful rule as we do this. So then the confidence interval for the 100 times 1 minus alpha percent confidence interval for proportion on this then is going to be simply that proportional value is going to fall within the range of minus z alpha over 2 and z alpha over 2. And again, this came out of the standard normal just like before. Okay, but the piece that changes is now this guy that's in the middle. Okay, so I'm going to take my estimator, subtract it from my true statistic, and then I'm going to divide it by what would be my standard error equation, which was this guy. Okay, and then all of that then is going to be equal to my 1 minus alpha. All right, and so that's kind of where we're going with this. So it's the exact same process. The formulas are just a little bit different, but everything else you do is exactly the same. You just kind of plug in, are you doing a proportion? Are you doing, you know, a regular confidence interval for the mean, so forth and so on. All right. Okay, so if we've got that, then we can kind of continue on with our proportion discussion and say that the confidence interval for our proportion can then be found as being just simply, all I'm doing is I'm taking that formula and we're rearranging it a little bit. That this is going to be my estimator plus z alpha over 2 squared, note squared on top of this thing, over 2n. Okay, and then plus or minus z alpha over 2, that's my statistic based on the size of the confidence interval I want, and then multiplied by this huge sum. Okay, and again, we're not going to worry about where this came from. I'm just pretty much just kind of showing you the formulas at this point. It's kind of beyond the scope of what we're trying to do in the series to derive this out for you, but just know that it is a different formula that has its roots in point estimation. Okay, and then all of that mess is over 1 plus z alpha over 2 squared divided by n. All right, sorry about that. I'm a little minor technical difficulty there, but we're back. So if we take our proportion confidence interval as this, you know, and then for n very large, okay, we can kind of simplify this thing down that you can see that any term with an n in the bottom will vanish on this. And so this and the formula then will simplify down to something that looks like our estimator plus or minus z alpha over 2 times the square root of our proportional estimate times 1 minus proportional estimate all divided by n. So it's a very, very simple formula, and it starts to look kind of like what we would expect. That this would be the standard deviation. Oops, put that hat on the wrong one. Would be the standard error of my estimator, okay? And so that will be our piece there. Okay, so again, it's pretty much straight plug and chug at that point. You take your estimate of the proportion and you go from there. All right, now there is one little thing that we've kind of talked about a little bit in the past, but I felt like we needed to kind of re-hit this a little bit. And this has to do with what we talked about with kind of how the confidence intervals are defined, okay? And one special topic that shows up, especially in things like experimental applications, is the concept of a one-sided confidence interval, okay? Before, I'm going to jump down a little bit. Before, we defined confidence interval as being something that looked like this, right? It was centered at 0. It went from a plus z alpha over 2 to a minus z alpha over 2, and my area was the limit that existed between these two guys. And what we would do is we would trim off the tails of both of these. Okay, this is what we did all along, but this is what we call a double-sided, because what happens is I take You know, if this was 95%, I would take 2.5% from here and 2.5% from here. I would split it evenly from the tails. Okay, a one-sided confidence interval is a little bit different. It requires a little bit of a correction. Okay, so this is what we call our lower side, in which we're looking for the probability of, you know, being less than some set value. And all of the area now, because again, this is still, the shaded region in this is still 1 minus alpha, just like we did before. But now, instead of trimming it off here, I put all of my area, including that tail in there, so that my z location changes a little bit. So if this is 1 minus alpha, then the area of the tail that we're looking for is alpha. Okay, which means then that if this location here was centered at 0, because we're still looking at a standard normal table on this, that my statistic is now at z alpha, whereas before it was z alpha over 2. So this value changes a little bit on a one-sided. Okay, so the moral of this is basically that all unclaimed area is located on one side now. Now you can have the flip side of this where the unclaimed area is a lower bound depending on the problem, and I'll show you that one here in a second. Okay, the rest of it, the construction is exactly the same, what we have, but in this case we're not really worried about the lower bound, and this comes up like in testing, and I give the example of, you know, you're doing some sort of strength test on steel, right? And as a designer, I want to know what the upper limit that I can count on is rather than the lower limit on this. You know, I'm looking for, you know, tensile stress greater than 30 KSI. I just kind of threw that down. You know, I don't care that the lower bound is 22.5, right? I just need to make sure that I can get to this because that's what I'm using to design for my maximum cases, okay? All right, so what happens is in this is that we have an upper and a lower bound for a 100 times 1 minus alpha percent. So it's the same process, just the shaded area has changed. So what I recommend you do when you're working these is first off, figure out if it's two-sided or one-sided. Usually that's given in our homework cases or test problems, it'll be given to you. Okay, but in practice, you got to kind of look at, but draw the picture. And what will happen is everything revolves around trying to find that value, okay, that z alpha, okay, or this value, that upper limit. And you'll see that it's a different coefficient. Okay, everything else is exactly the same. Okay, all right. So if we do this, then if everything is on the lower side, which is the case that I just showed you in the picture, we're going to have our population mean is less than x bar plus z alpha times s over square root of n. Again, this term doesn't change; it's exactly the same. Everything's on the lower side. Okay, but you can also have everything on the upper side, depending on a minimum bound if you want to construct a problem that way. And in that case, the lower bound, it should be no surprise, is the population mean is going to be greater than x bar minus z alpha over s square root of n. So what happens is before we were writing everything as kind of this plus minus, and so now we're just basically splitting it and throwing all of the area into this z term on one side or the other. That's all we're doing as we're trying to look at that. And so we're going to construct things accordingly. All right. So on that then, that will give us all of our area on the upper side. So, all right. Okay, now let's take a look at some more types of distributions that we can look at. Okay, and so if we look at what we have here, we have our normal distribution for population intervals. Okay, so confidence interval for the population mean. Okay, again, this is what we had before, way back in the beginning. All right, x bar plus or minus z alpha over 2. Now again, we're back to the case where I needed to know the standard deviation of the population. Now this guy is more accurate than the sample one that we just showed you, but it does have the restriction that I have to know this. Okay, so the requirements to use this formula, if you recall from our last video, was that x bar, okay, is a normal distribution on this, and again, central limit theorem bails us out of that, basically meaning n is some large, and population sigma is known. Okay, or we can look at the one that we just created, and which is now x bar plus or minus z alpha over 2 times s over the square root of n. Okay, and now what happens in this is that the requirement, while the requirements here were very stringent, okay, I had to have a normal distribution on x bar, and I had to have a known population standard deviation. Okay, now the new formula that we're dealing with will work for any distribution as long as n is large. Okay, and so what has happened in this is not only have I lifted the requirement on the normal distribution, but I no longer require the population standard deviation. Okay, and a lot of that comes because I can do that with the central limit theorem. So that's pretty cool, okay? And in general, as we talked about, this is easier to compute because if I've got the sample data to get this, I've got the sample data to get this. Okay, but the problem becomes, what if neither one of these cases is right? What if I wanted to know, the scenario where sigma is unknown, the population standard deviation is known, or n is very, very, very small? Because remember, for n to be large, we were saying that n was greater than or equal to 30. It's kind of the rule of thumb on there. But now, what happens if neither one of those cases is true? Well, then neither one of these works, and so we have to come up with a correction to be able to work on this. Okay, and so our general idea that we're going to work on this is, what is the confidence interval for a normal distribution, sigma unknown, any size sample? Okay, and so this leads us to a new distribution type, okay, what we call the t distribution. Sometimes they call it as the student t. Okay, and so what they're going to do is they're going to define a new statistic t as simply being x bar minus mu over s over square root of n. And if you look at that, that's basically the same formula we were using for z. Okay, this is called the t-statistic and is used for estimating mu from x bar when sigma is unknown and n is less than 30. So what happens is instead of going into, before we were playing with, the z, and that took us to the standard normal tables. Okay, now we're going to play with t, and we're going to go into the t distribution tables. Okay, and so it's a different set of tables, it's a different set of data that have been generated to help us with those area calculations. Okay, now, we say that this random variable t has a t distribution with n minus 1 degrees of freedom. Okay, so it's kind of a measure of how many points do you have that are helping you establish this criteria. Okay, now the thing that's kind of cool is that if n is greater than 30 on this, we don't need to do this. We can just approximate it as a z distribution because the central limit theorem will allow us to do that. It's the case where n is less than 30 where the central limit theorem breaks down. And that's why we have to do something a little bit different for these involving the t-distribution. All right, so let me show you what a t-distribution looks like, and then we'll show you the tables, and we'll kind of play with those a little bit. Yeah, the process itself is very, very similar. Okay, so the properties that we have, and so what I've done is I've drawn, again, I draw it as a bell shape. It's not truly normal, but it is kind of humped in the middle. And it's, it could be a flat bell or a tall bell or whatever. Okay, that it's centered at 0 again. So it's kind of like the standard normal table. It's bell-shaped. Okay, and then as the parameter that changes is that this distribution changes as this new factor, okay, and this guy is just n minus 1. Okay, so as I increase my sample, as this guy increases, that TV value will start to decrease, which means that your error starts to get smaller and smaller and smaller. Okay, so again, we're going to define this new character as n minus 1, and when I say new, that's this guy, the Greek letter nu. Okay, n minus 1 degrees of freedom, and then this statistic, t statistic, at that point nu represents the values of t. Okay, so this is kind of a moving target, if you will. Okay, so what happens is the critical values can be found for small values of alpha in our table A5. So let me pause the video and I'll pull out the book and we will look. All right, so what happens is we can pull up these critical values for t distributions. Okay, and again, if you look, this looks a whole lot like our standard normal tables. Okay, the one thing to notice though is that the areas that are being computed on the standard normal are the areas of this tail region. So if you want something less than this statistic, you'll have to do the complement, the 1 minus. So watch the shaded area. That's one reason they gave you this picture. Okay, so again, it's a one-sided distribution. The shaded area is completely on one side. And then this is our distribution of our statistic curve for our t-nu density curve. And it's really easy to work with. Okay, so we have a bunch of different alphas that are established. So here's my 5%, here's my 1%, here's our really, really small ones on those. And then all you do is you go in and you pull off your degrees of freedom, and this becomes your t-statistic. So if we wanted, say, 4, a degree of freedom 4, meaning your sample size was 5, my t-statistic would be 2.132 on this. And that will give you the t-statistic that will help you calculate that area up on that point as well. Okay, all right. So that's where we're going with that. We're going to start using a lot of different tables going forward in the videos, but they all have their own special purposes. So that will get us our critical values for small values of alpha. Okay. Now, one thing to point out is that the values can also be found in our table A8. So let me pull that one up. Okay, and it's more of the general, those are the critical values. If I go to A8, okay, we're getting into is more of the tail areas. kind of thing, that if I have my t-value statistic, if you will, what we pulled out of A5, I can, if I know the t, I can read this exactly the same way. They know I have a t of 2.0, and my degrees of freedom, again, this is n-1. I come down and I can pull the values out, and this becomes the area associated with that tail region. Okay, if I look, say let's do 0.5 and do 5. Your tail area would be 0.319 is the region of the tail area that's up above that. And with that, then I can start making some estimates on those. So it's just a different table for the case where n is small or where sigma is not known on those. All right. Okay, now for a rule of thumb, one thing to remember is that if t is infinity, if we have an infinite number of degrees of freedom, this becomes our standard normal distribution curve. Okay, and so for a lot of times, though, because of some differences, they say that if your nu is greater than 40, then it's basically standard normal. You might as well just be using that. Okay, so it's a little bit of a different value they recommend on the student t. Okay, and as you get smaller and smaller n, that distribution changes more and more and more. Okay, but that's our nu for the t distribution. As kind of a rule of thumb, is considered a large sample for t distribution type of stuff. All right, the confidence interval then should be no surprise then, is that it's going to be x bar plus or minus, and then here becomes that t alpha over 2 n minus 1. So that's a double-sided scenario, and then we're just going to multiply by standard deviation sample over the square root of n. So again, the formula doesn't look any different. It's just a different table for when n is smaller, and those are some of our basic t distribution properties as we start to kind of look at that. Okay, so I've got an example that we'll kind of work at here. I'm going to jump down. I'm going to split this video because we're getting a little long, but at least want to get this in here, okay? That we have an example of the ability of individuals to walk a straight line. Now, again, I don't know how they're qualifying this, but it's kind of an interesting problem. And the data that we're given is that n equals 20, sum of xi equals 18.51, sample mean is taken as 0.9255, and then they do some math and provide some other data statistics. And so I've calculated the sum of xi squared is 17.255, and then this variance term, this sxx, is going to be this term minus this guy squared divided by n gives you a number of 0.124495. Okay, and what this does, if you remember way back on like the very first video in the series, we said that you could write the variance as being this parameter, sxx, all over n minus 1. Okay, so that gets me s squared, and then s becomes this number here, so 0.080947. Okay, all right, now what we want to do is we want to be able to find a 95% confidence interval for this scenario, right? Okay, so we know that n is 20, and that's less than 30, so we're not in a standard normal table anymore. We're going to have to use the t distribution table. All right, and so we know that our formula then is t alpha over 2 and n minus 1 times s over the square root of n plus the x bar, plus or minus. And then for, say, a 95% confidence interval, 100 times 1 minus alpha is 95, so alpha is 0.05, and then alpha over 2 is 0.025. And then with that, I know that my degrees of freedom then is n minus 1 or 19. Okay, so all I have to do then is go back in and pull up my table A5. Let me pull that up again. I should have left this open. I apologize. That's what you want to see, is me flipping through a book, right? The page flipped over here. All right. We come back up into this guy, and I'll get this up far enough, hopefully. All right, so if you remember, what we're looking for is alpha of 0.05. So we're in this column. We're going to come all the way down here to number 19. Okay, or sorry, t alpha over 2. I want the 0.025. Okay, so that's one of the things that we got to kind of look at here, is that, remember the formula, and again, I've warned you a couple of times, got to watch the subscripts, and here I didn't watch the subscript. They want the t alpha over 2. This is a double-sided. All right, so if my alpha is 0.05, then my alpha over 2 is 0.025. That's why we're in this column. So 0.025, I come down to number 19, and I get this number, 2.093. And that will be your statistic that you use to establish your confidence interval. So if we come in and we look, that's where this number is coming from. All right, so then once I do that, I can plug this in. So that number here is all one statistic. 2.093 goes into here, and then x bar plus or minus s over the square root of n gets me this confidence interval. So this is a little bit different based on the sample size, because now, because the samples are smaller, I'm less confident. This thing has to grow in width compared to what you would have found on the standard normal table. So, in fact, if you remember, for a double-sided 95% confidence interval, we can flip back real quick and go over here. The statistic that we're looking, again, for a double-sided, we'd be looking for an area of 0.975. We did this in one of the last videos, but I just want to show you the value. You'd be looking at this guy right here, right? And so the number that we had was 1.9, and then it'd be 1.96 would be that number. So if you compare that on here versus 1.96 equal to Z alpha over 2 for the same confidence interval, you can see that it grew a little bit. It grew about 2% based on the sample size. And this number changes based on whatever your sample. If this thing gets smaller, then clearly my statistic will change as well as we start to kind of look at those. But that's kind of one of the things that you can start to notice is that just we're less confident because I don't have as many samples to support my idea. So we had to make a correction, and that's kind of what we're looking at. All right. So with that, we'll go ahead and we'll stop there. I'll come back to this example in the next video when we'll talk about some of the other interval types. Okay, so hopefully that made sense to you. I apologize for the book flipping and the technical glitch at the beginning, but I'll fix that. And then hopefully that all makes sense for now. So as always, leave us some feedback down below in the comments. And then as always, like the video if you liked it, and please be sure to subscribe to the channel. Otherwise, I hope you're having an awesome rest of the day, and we'll talk to you all later. Happy engineering.